Okay, so this is the E2 question of worksheet 3, and this is questions about cosmology. The diagram below represents a spherical region of space based on Newton's model of the universe. Earth is at the center of the region. The dark line represents a very thin spherical shell of space at distance r from the Earth. So, with reference to the diagram and Newton's model of the universe, explain quantitatively Olber's paradox. So this quantitative means that you've got to do it within numbers, formulas, and so forth. Now, we know that firstly, when looking at this is 4 marks, so we need to make sure that we give all the information required. You need to basically at the beginning set out what is Newton's model. Well, Newton's model was that the universe was infinite in size and number of stars. Also that it was static and it was universal. Alright, it would last forever. So on the basis of this, what Olber basically said was that these stars in this shell, it's a very thin shell, these stars within the shell, I'm just redrawing it a little bit here, if this was the distance there would be x, which is very small in comparison to the r. We know that the volume of that, the volume would equal 4 pi r squared, which is the surface area, of the inner shell, times the x, and so the volume is proportional to r squared, and because they are there's an infinite number of stars and that they are evenly spaced, it's a uniform. This is important to add into this. It's uniform. There would be stars scattered about uniformly in this region. Therefore, the bigger the volume, the greater the volume, the greater the number of stars. Therefore, the greater the luminosity. So the luminosity is actually proportional to r squared. But as we move out, we know from our law that the apparent brightness is proportional to 1 over r squared. So we have that the amount of radiation reaching the Earth is proportional to 1 over r squared, and the luminosity is proportional to r squared. So these actually cancel out. So as we add shell upon shell here, if I add another shell on next to this around here, let's call it the green shell, and if it's got the same x thickness, that would add on another amount of light, the same amount of light that the first shell, and so it will just keep on adding on, and this is for infinite, and so it would become infinitely bright. So your night sky would be bright. So you need to put that in here. So you basically would need to show your number of stars is proportional to r squared, but the brightness, the apparent brightness, I'll just call it B, is proportional to 1 over r squared. So we have that stars in the distant would provide light which would continue to add on. Okay, and the sky would always be bright. So that was the idea with Olber's paradox. Now going on to this final question over here. Explain how the Big Bang theory provides a resolution to Olber's paradox. Well, the Big Bang theory states that the universe had a beginning, at a beginning. It is not static, but expanding. It's not uniform, and it has a, it therefore has an end. It's not infinite. It's not infinite. So we wouldn't have this adding on and adding on effect as we would have with the Newton's model. Okay, thank you very much. That's the end of that worksheet.